Let's look at the notes for Lesson 2, Exploration 2, which is about connecting force and motion. We're going to start with recognizing some patterns from the previous exploration. We finished with an experiment where we tested different materials and saw how the type of material would affect friction. Friction is a force. So whenever an object is pushed or pulled across another object, like when we have a box sliding down a ramp, in our experiment, we had boxes sliding down ramps. The boxes were made of different materials, and the ramps were made of different materials. So whenever there's sliding, there is friction. If you add up all of the vectors that are acting on that object, then you're going to get the net force acting on that object. Now, if we look at this image where we zoom way in on the surface, but on the surface where the box contacts the ramp, or the inclined plane is the term that was used, we can see that even if it seems pretty smooth, it's at a microscopic scale, it's going to be pretty rough. Most objects are. And the roughness, each of those little bumps and hills is going to create a force that resists motion. If the object is sitting still on that ramp, we call that static friction. If the box is sliding down the surface, we call that kinetic friction. When we look at this at a very zoomed in scale, we can see that there are little rough parts on the box. But if you imagine it on a larger scale, if you tried to slide two pieces of sandpaper together, they wouldn't slide against each other very well. Whereas if you tried to slide two pieces of glass together, they might slide more easily, especially if they had some kind of a lubricant in between them. If you stand on one side of a cart and you push on it, and your friend stands on the other side of the cart, and you both push, sort of a reverse tug of war, then if it doesn't move, if it was not moving and it continues to not move, we know that the forces must be balanced because the cart is not accelerating. It started with zero velocity, it continues to have zero velocity. If you are pushing a cart, let's say you're pushing a shopping cart through a store aisle, you're applying a constant force, and so the cart is moving at a constant speed. You're not speeding up, you're not slowing down, you're just walking down the aisle with a cart. If it's moving at a constant velocity, then we know that the net force on it must be zero. So here's the cart. Oops, that's not a cart. Oh, I'll make it into a cart. Okay, so here's a cart. It's got some wheels. Here's you pushing it along. You are applying a force to the cart. That's the applied force. And the cart is not accelerating. So that means that it must have a force in the opposite direction that is the same magnitude as the applied force. And that force is going to be the force of friction. You see these two forces add up to zero. So the cart moves at a constant velocity, which means no acceleration. It just moves forward at a constant velocity. Those forces balance each other out. These are balanced forces. If you have a net force acting on the object, you're going to have a change in motion. So if, for example, you decide to race your friend to the parking lot, you're pushing that cart. I know it's a very large cart. Then if you start running and applying more force, and the force of friction is still the same, if you apply more force than the force of friction, so your applied force is greater than your force of friction, then your acceleration is going to be greater than 0. So let's look at some examples from your book, and you should have the same responses on page 30. Oops, let's get rid of those drawings. Okay, if a car is parked, then it's not accelerating, right? Its velocity is 0. It remains at 0. That means it's not accelerating. If a car moves at a constant speed of 100 kilometers per hour on a straight roadway, like on the freeway, then it's not accelerating. Okay, you could be going really fast. If you're going 100 kilometers per hour at a constant rate on the freeway, you're still not accelerating because you're going in a straight line and you're going at a constant speed. If a car slows down in a school zone, then it is accelerating. The acceleration is opposite the direction of the velocity because it's slowing down. It's changing its velocity, so it's slowing down. If a car is stopped at a red light and then begins to move when the light turns green, then it is accelerating. And in that case, it's speeding up. So the acceleration, the direction of the acceleration is the same as the direction of the velocity, forward, in the case of a car speeding up. If a car turns a corner at a constant speed of 10 kilometers per hour, it's accelerating. Even though its speed is not changing, its direction is changing. And remember, acceleration is any change of velocity. So we would say that the acceleration, if the car, let's say here's a corner. Oops. Here's a corner. Here's a car. So it turns left. We would say the acceleration is, well, we'll learn about this more a little bit later, but when it first starts turning, its acceleration is to the left because it's changing direction to the left, and its velocity is changing as it moves through that curve. So its velocity gradually changes from forward or up to left. Okay, and the acceleration, we'll talk about acceleration a little more later because it's a little more complicated than just saying accelerate. It accelerates to the left. Friction, when an object is moving, typically friction is the force that acts against that motion. It is possible for friction to accelerate an object in the direction of motion, but that is a special case. So typically we say friction acts against motion. Friction is a force. So force is a vector quantity. So friction has both direction and magnitude. If the friction is low, then that means that it takes less force to keep something moving against friction. That's why if you go ice skating, there's low friction between the skate and the ice. You'll just keep going. It doesn't take a lot of force to keep moving. That's why I could never ice skate, because I would move when I wouldn't want to. If you have greater force of friction, like if you have hiking boots on a dirt trail, you're going to have a greater force of friction, and you're going to be less likely to slide, right? Because you have that great force of friction working against your sliding. If you could reduce friction all the way to 0, and that was possible on the lab that you did, where you could have a frictionless ramp, then an object sliding on that frictionless surface would continue to slide at the same speed in the same direction until some kind of force acted on it. So it would continue sliding in a straight line at the same speed forever. This is part of Newton's first law. An object at rest remains at rest, and an object in motion continues in motion with constant velocity unless the object experiences a net external force. Here we see two hockey pucks. So here we see a hockey puck on the left that's not moving. And the reason why we use hockey pucks in this example is because hockey pucks they're very smooth, so they have a very low friction, very low coefficient of friction is what we call it, and they're on ice. So ice also has a very low friction. So there's very little friction between a hockey puck and ice. And if you've ever watched a hockey game, you've seen that when the hockey players hit the puck, it will keep sliding for a pretty long time, bouncing off the walls. So if we draw a free body diagram for a hockey puck that's not moving, a free body diagram includes all of the forces acting on that object. So we have the force of gravity pulling it down. The weight of the puck is pulling it down. And then the ice, the surface, is exerting an equal force in the upward direction. And that force is perpendicular to the ice, and it's called the normal force. We saw this in the last exploration. The normal force is always perpendicular. And if the object is not accelerating, then that means that these forces have to be balanced. So the normal force is going to be equal and in the opposite direction of the force of gravity. When a puck is moving at a constant speed in a straight line, now what forces are acting on it? Well, it has the force of gravity acting on it. Let me get rid of my face there because it seems to be in the way. Okay, so we have the force of gravity acting on it. We have the normal force pushing back up on it. Is there any other force acting on this? No, there's no other force acting on it because it's moving at a constant speed in a straight line. So it's not accelerating. This is a puck that's moving. So yes, it has velocity. It's moving, but it doesn't have any force pushing it. Now, in real life, if we assume there is some friction, okay, there would be a little bit of force of friction here. Force of friction. But if we assume that it's on a frictionless surface, then there would be no force pushing it forward. That's the point that's being made here. Here's another free body diagram. This is a free body diagram for this Atwood machine. We experimented with these in class. An Atwood machine has, in class when we had our Atwood machines, we had mass hanging down off a table. So it wasn't over, they weren't both moving in vertical directions. One was horizontal, the other was vertical. We called it a modified Atwood machine. But in an Atwood machine, you have two masses attached by a string that runs over a pulley. If we draw a free body diagram for each of those masses, it would look like this. Each mass is pulled down by gravity and up by the tension in the string. So the string is exerting this force of tension on the mass. Gravity is pulling the string down. And you can see that tension and gravity act in opposite directions. If you have the Atwood machine set up in a way that the blocks do not accelerate, then the force of gravity and the force of tension are going to be equal to each other on both blocks. Here we have some data that was presented to you in your book. We're going to graph it and draw the line of best fit. So let's graph it. We have, always look at the labels on your graph. Always look at what the x and y axes represent. So we have force versus acceleration. When we have a force of 5, we have an acceleration of 2.5. So there's a data point there. When we have a force acting on this block, when we have a force of 10 newtons acting on this block, we have an acceleration of 5. Okay. When we have a force of 20 newtons acting on this block, there's an acceleration of 10. Wait a minute. 5. Force of 20 newtons acting on this block, there's an acceleration of 10 meters per second squared. And when there's a force of 30 newtons on this block, there's an acceleration of 15 meters per second squared. If we want to draw a line of best fit, Drawing lines is challenging for me. Let's, well, I'm going to draw a messy line, and I apologize for the messiness of my line, but pretty soon I'll learn. This drawing on tablets is pretty new to me. There we go. There we go. There's a line of best fit. Now, normally a line of best fit doesn't need to touch all of the points. In this case, it does because our data was idealized. What do we see? We see a slope. Okay, when we see a slope in a positive direction and it does not change. So this tells us, what does this tell us? This tells us that, the positive slope of the force acceleration graph shows a direct relationship between the force on an object and its acceleration. A direct relationship means that when one increases by a certain factor, when one variable increases by a certain factor, the other variable also increases by the same factor. So when the force doubles, the acceleration doubles. A larger net force on a given object produces a correspondingly larger acceleration. Here we see a diagram of a car where these dots represent where the car was at even time intervals. So we can see if the car is accelerating or not. The greater the force on an object, the greater the acceleration. So the acceleration, A, depends on the direction and magnitude of the force F. So let's draw this. We want to draw the vectors. So these show... These blue vectors that are already drawn in show the car's velocity before and after the time t. And the dots show the car's position at equal time intervals. So the blue lines, the blue vectors show the velocity. We're going to draw a vector showing the direction of the net force. Okay, so the direction of the net force in the first one, we can see the dots are getting farther apart. So the car is accelerating in a forward direction. So that means that the force is in the same direction as the velocity because it's causing the car to accelerate in a forward direction. Okay, here we see a car slowing down. So the force is going to act in a direction opposite the velocity. It's causing that acceleration. Remember, force, unbalanced force, net force causes acceleration. Here we see another car that's slowing down. I'm going to draw the vector above it just to make it easier to see. So we have a force acting in the opposite direction because it's slowing down. And on the bottom drawing, we see a car speeding up. We see a car. Actually, I'm sorry. I messed up on the second one. Okay, so on the first one, let's do that again. On the first one, we see a car speeding up, so the force is acting in a positive direction. On the second one, the velocity vectors are in the negative direction, so that means it's speeding up in reverse. It's speeding up in reverse, so it has a net force pushing it backward. In the third one, we see it going forward but slowing down. And so it's slowing down, so it has a net force slowing it down. The net force is opposite the direction of motion. And here in the last image, we see it going in reverse, but also slowing down. So that means the net force is in a forward direction. Notice the direction of the force is the same as the direction of the acceleration. We already did some exercises where we looked at direction of acceleration versus direction of velocity. Well, remember, the force is causing the acceleration. So the direction of the force is going to be the same as the direction of acceleration. Here we see some more data. We're going to graph this again. Here we see force in newtons. But what does our graph show? Our graph now shows acceleration versus mass. So the acceleration, when the acceleration of this object is 10, or we can say when the mass of this object is 1 kilogram, its acceleration is 10 meters per second squared. When the mass is 2.5 kilograms, its acceleration is 4 meters per second squared. When the mass of this object is when the mass of this object is 5 kilograms, its acceleration is 2 meters per second squared. When its mass is 10 kilograms, its acceleration is 1 meter per second squared. And when its mass is 15 kilograms, its acceleration is 2/3 of a meter per second squared. Now, if I had trouble drawing that last line, how about now? Because this best fit line is not a line, so I can't use my ruler. Maybe I'll do a better job if I don't use a ruler. So here we see it's a curve. It's a curve. And we can see that it's a curve in a negative direction, but it's becoming increasingly positive, or it's approaching 0. Okay, we're going to select some terms to complete the statement the same way we did last time, because what does this show? This shows that as the mass increases, what happens to the acceleration? As the negative slope of a line tangent to the mass acceleration graph shows an inverse relationship between the mass of an object and its acceleration. A more massive object acted on by the same net force as a less massive object has a smaller acceleration. Okay, so when you use the same force and increase the mass, you're going to have less acceleration. Here's a summary of what we learned. We learned that as the mass increases, the acceleration decreases. We learned that as force increases, acceleration increases. So this can be summarized in Newton's second law, which states force equals mass times acceleration. As the force is directly related to the acceleration, and inversely, and the acceleration is inversely related to the mass. So this gives us a formula that summarizes Newton's second law. F equals ma.